Nada mais jovem. Falei que eu não posso abrir o prometido. Pode começar? Espera, mais o olho.
All right, so we can start, right? We can start, right?
Yes.
Yeah, okay. All right, welcome back. Yesterday's problems were quite a lot harder than the day before because it was a Polish sub-regional and the day before was Czech sub-regional, so you can see clearly the difference between the problems the Polish solve and the problems the Czech and Slovak solve. There weren't any completely trivial problems, so I'll start with problem A, which was kind of standard. It wasn't definitely not the easiest problem in this contest, but it was a nice standard problem. So, all right, we have some vending machine with n types of sweets or whatever, n is sufficiently small. Let's say up to 40, and each product in this vending machine has a cost CI, and there are WI of these products in the vending machine. And what happens is that when we buy product K for price CI, we also have some let's call it B money, which is up to 64,000. These numbers are also approximately up to 40, and you can notice that 64,000 is 40 to the power of 3. So it's a strange coincidence, and it seems that this B 40 to the power of 3 is the obvious upper bound on how many sweets we can buy, but we'll get to that later. On the money we can buy, we can pay for all the sweets in theory, but actually the vending machine has a bug, and when we buy sweet K, then also the vending machine gives us sweets K minus 1, K minus 2, up to 1, and this is for the price of CK. So instead of paying CK plus CK minus 1 plus CK minus 2 etc up to C1, then we only need to pay CK to get all those K sweets. And what we want to do is, since we have only a limited amount of money, we want to buy sweets with the total maximum price. So if we bought a sweet CK, then we paid CK money, and we got sweets with prices CK plus CK minus 1 plus CK minus 2 up to C1. It doesn't matter that we actually paid for it. We're only interested in the maximum price of all the sweets, not minus the price we actually paid for it. That would be an interesting variation on that problem, but actually kind of similar because the prefix sums would just be smaller by the last element. So how do we solve this? The first thing to notice is that it doesn't really matter in which order we buy those sweets. If we decide to buy sweets K to up to K, let's say M, then it basically doesn't matter in which order we buy these sweets, because when we buy Ki, then it costs us C Ki, and we gain sweets with a total price of C Ki, and this doesn't matter on the order of those operations, on the order in which we buy those sweets. But there is one more thing in the statement, that it isn't possible to buy a suite with. It isn't possible to just try to buy a suite K if there are no more suites of this type K left in the machine. So it isn't possible to just try to buy. It is possible to buy a suite K if there are some suites left in this machine, and for example, if there are no suites of type K-2 left, then the machine just will give us a suite K, K-1, nothing of K-2 because there is nothing left, K-3 up to 1. But if there were those suites of this first type, the type Y left, then it would give an error. It isn't possible to buy. To just buy nothing of this type and something of these types. And this gives us a small constraint on the order in which if we bought, if we, for example, had K1 greater than K2, then it is possible that we would buy a suite with type K1, get K-1, K1 minus 1 up to 1, but then there wouldn't be any suites of type K2 left, because it's possible that we just got the last suite of type K2 when we bought a suite of type K1. So we don't want this, but if K1 is smaller than K2, then there is no such problem. We can just buy suites of this type and all smaller types. If there was at least one suite of this type, and then if there was one suite of this type left before this operation, then it will also be left after this operation, because we only got suites of types K1 and smaller, and this one is larger. So this is fine if there are at least as many suites of a given type initially as there are in this sequence. And if this sequence is non-decreasing, of course, if K1 equals K2, then it doesn't matter in which order. So we want to buy those suites, the ones for which we actually pay, in a non-decreasing order of their types. And this gives us a dynamic programming solution where for each state we want to remember how many suites that we are at a suite of type I. So this is the current type of the suite we are processing, and we only want to buy suites of types I and greater. We already bought all suites of smaller types we wanted. Then we have some B money left, or we paid B money, it doesn't matter since we just check it against the uppercase B. And we want to buy some J suites of types I plus 1 up to n. So we already predict that in total, when we buy suites of type I, suites of type I plus 1, and so on up to n, the ones we haven't yet bought any suites, the types we haven't yet bought any suites from, then there will be in total J of them bought. This tells us that it doesn't matter what types of suites we decide to buy, but the number of suites of type I we get will always be equal to J, because whenever we buy a suite of type I or greater, then the number of suites we get is the suites of type I we get is 1 all the time, so the total number is J. So this is the state. There are a total of O n times B times this number can be only up to max W squared, the maximum number of max W times n n times b times n times maximum number of suites of one type, because I is up to n, b is up to uppercase b, and the number of suites we can buy in total is only bounded by this number, because we buy up to maximum W of each type. Of course, there is no point in buying too many of these suites, because if we buy more suites than this Wi, then we still get just Wi suites of this type I. So we can optimize this and just treat all suites of just treat states where we buy J suites where J is greater than Wi as sort of one state. And now, how do we do this dynamic programming? Is that if we have this state, I, B, J, then we can buy some K suites of type J, of type I, and get to a state I plus 1, B plus K times Ci, and J minus minus K. Yeah. And this is with how did I call it? It's total cost is of both suites is increased by K times total cost is increased by minimum of J and Wi times Ci, because this is the number of suites of type I we got, and each of them costs Ci. Of course, for each state we are interested in the maximum cost of both suites, of obtained suites. So this maximum cost is increased by the total cost of up to J obtained suites of type I. What happens is that when we buy exactly K suites of type I, then there are J minus K suites left of types I plus 1 up to n to buy. The amount of money we have to pay for it increases by K times Ci, because we bought K suites of type I. And we move on to the next type of suite. So there are this many states. For each of these states we try all K up to Wi. Of course we cannot buy any greater number than Wi suites. So the time complexity of this is O number of states times max W, n squared B max W squared. And since B is kind of large, this can be slow. Fortunately, n is sufficiently small, max W is sufficiently small, and this would be something like 40 to the power of 2 plus 2 plus 3, so 40 to the power of 7. This is too much. We can put one obvious 40 from this by realizing that we only need to buy up to max W of those suites. Total number of bot suites is up to max W, because when we can afford this, when we have B max C times max W, then what happens is that we look at the nth suite and buy Wn of those suites. So we buy all suites of type n. Then we look at suite n-1, and if Wn-1 is less than or equal to Wn, then we already got all suites of this type, so nothing happens. We move on to the previous suite and so on. And when we encounter a suite where Wi is greater than Wn, then there are finally suites of this type that we haven't gotten all of them. So we just buy what's left over, that's Wi minus Wn, and then we move on again to Wi minus 1, check if it's greater than Wi, and if it's smaller, then again we already must have gotten all suites of this type. If it's greater, then we buy up all that's left, and so on. And like this, we only buy max W. The total number of bot suites is just max W, because we found a decreasing sequence, some Wi1 greater than Wi2 is greater than Wi3, and so on is greater than Wn is a sequence that always ends with n, with the nth suite. Of course, if it's greater than 0, and we bought this many suites of this type, ATC, Wi2 minus Wi3 suites of type I2, and so on, and suites Wi1 minus Wi2 suites of type I1. So it's in total just Wi1 sweet spot. So if B is greater or equal to this number, then actually we can just buy this many suites, just Wi1, and we actually get all the suites from that machine. So we can bound B not by 40 to the power of 3, but 40 to the power of 2. This is up to 40 and this is up to 40. So instead of 40 to the power of 7, we would have O n squared max C squared max W to the power of 3, and this is 40 to the power of 6. And this should be still too much. It would be better if we got 40 to the power of 5, and that's why we bound that total number of bot suites J by sufficiently small numbers, since if it's possible that we don't have enough money if this b is sufficiently small, but it's always true that if b is greater than j times b is greater than max wj plus 1, wj plus 2 up to wn times the maximum price, then it's always impossible to buy that. But yeah, as I mentioned, we just find some suitable scheme to keep that number of bot suites sufficiently small. So if j isn't bounded by n times max w, but j is just bounded by max w, if we have a greater j, then we just bought all the suites. Then the total number of states is instead n times b times max w, or since we bounded b by max c times max w, then it's n times max c times max w squared states, and the time complexity is number of states times max w, so it's n times max c times max w to the power of 3, and this is 40 to the power of 5, which is 6 million times 16, some 40 million, 60 million, something like that, and this is doable. It's possible that just without bounding this number j by max w, it would still be doable, just pushing through this dynamic programming, because a constant of 40 isn't much. There would be some states we don't have to consider most likely, and dynamic programming has a very good constant. So yeah, this was problem A. And now let's move on to something simpler. Problem D was about taking some string S1 to n and making another string, let's call it R1 to n, such that the lowest common subsequence of S and R is minimal. And this is actually a quite simple problem, despite how it looks, because longest common subsequence is something that can be quite complicated to compute if we can just completely change everything in this string R. It can happen that if we decide to skip some character, then at some position have a bigger longest common subsequence. But in this case, we just need to notice that if there are four characters, 4 letters in this string S, and we also need to use these 4 letters in string R. And let's just say that the character A, for example, appears C8 times. Then it's always possible to create a string with at most with LCS at most CA. And this string is just the character A repeated n times. That's kind of obvious that we don't need to add anything else. If there are just this many characters of this type, then we can always create a string that only has these characters as the longest common subsequence. It cannot be any greater than CA because there are only CA characters in this string. So it doesn't matter if we put all characters A in this string we want to create. So if we had some character that doesn't appear at all in this string, we could just make this string contain only that character. If each character appears at least one time in this string, we could we could just replicate it always in this string, and we would have It's also impossible to make an LCS that contains less occurrences than that LCS to create a string R that has an LCS with length smaller than the smallest number of occurrences of some character, because the smallest number of occurrences of one of those 4 characters will be at most n divided by 4, so CA, CC, CG, CT is at most n divided by 4, because of the required principle, the pigeonhole principle, that if we had more than n divided by 4 of each of these characters, then we would have in total over n characters in total. And the smaller, the minimum of this is up to n divided by 4, and in this string we will always have at least this minimum of some character, because if each character A, CGT appeared less than this number m times in string R, then we would have in total we would have less than 4m characters in string R if each of them appears less than m times. And since m is at most n divided by 4, then this is smaller than n, and it's impossible because we need to have at least n characters. So there must be some character in this string that appears at least m times, and this means the LCS will be at least m, because there is a character that appears at least m times in this string, and each of these characters appears in this string at least m times. So there is a character that appears in this string m times and in this string m times. So there is a longest common subsequence that has length at least m. And this gives us a construction, because it must be, the answer is at least m, and we can create an answer equal to m if we just take the character out of these 4 that appears exactly m times in this string S, and use only this character in string R. This is what I was talking about here, that if A appears CA times, if CA is equal to m, then we can create an LCS that's up to CA, so equal to m, and the LCS has to be at least m, so the answer is always m. Then there were two more quite easy problems. Problem J was most likely the easiest. It was about scheduling that we have some intervals in time. The I interval has length Li, and its final time has to be less than or equal to Ti, so its end has to occur at time Ti, and we want to find out if we schedule some of these intervals in such a way that they don't overlap, for example, like this. Then we want to find out what's the maximum possible time at which we start the first of these intervals. And this is quite simple because we just need to order these intervals by this finishing time. If there is an interval with finishing time smaller, if this interval, for example, has finishing time smaller than this interval, then we can just swap them and nothing bad happens. This rules that each interval has to finish before its finishing time. Will never be violated by this. So we just look at the interval with the last finishing time, decide that it can end at this time Tn, and it has length Ln, so it will end at so it will start at time Tn minus Ln. And then we can schedule all previous intervals at times smaller or equal to Tn minus Ln, and also smaller than or equal than their own finishing times. So for interval n minus 1, we just schedule it at time min of Tn minus 1, Tn minus Ln. This starts at this minus Ln minus 1. So we schedule interval n minus 2 at time min of Tn minus 2, and this time this min minus Ln minus 1, which is the time when this interval starts. And this interval, we already decided that since they're sorted by Ti, so Tn minus 1 and so on. So this interval has to end at Tn minus 2 and this. And so we just schedule all intervals from the last one to the first one, and find out when the first interval starts, and that's the answer. Then we have problem I, which wasn't in the contest actually, because it just isn't in any online judge, and there is no way to do anything about it because I don't have test data or anything. But I'll just explain its solution because it's also quite simple. The problem is that we have an array of numbers a1, a2, say a minus 1 n minus 1 an, and we create a graph where we have a I greater than, all those numbers should be distinct. If we have ai greater than aj, then there is an edge between vertices I and j. So it's an inversion graph, so to say. And we want to find out what's the number of connected components of this graph. There is a standard solution that just uses DSU union find, and we just keep so far found. We just process these numbers in this order. Keep so far found components, so far found connected components, and for each connected component we just remember what was the largest number in it, since if there will be an edge from that component to some number, then it will always be from, then there will always be an edge from the largest number in that component to this next number. So let's say we process this AI, and so far we have found some S1, S2, and so on, Sk, and then we want to process AI. So these numbers are the maximum numbers in each connected component found so far, and they are sorted in increasing order. Yeah. Si is smaller than Si plus 1. So let's look at Sk. If Sk is greater than Ai, there is an edge from Sk to Ai, and we can merge these two components. Then we can look at Sk minus 1. If Sk minus 1 is greater than Ai, then there will always also be an edge from Sk minus 1 to Ai. And since Sk and Sk minus 1 are maximum numbers of different components, then there is an edge from this to this, there is an edge from this to this, and so these two become one connected component. So we are just adding some relevant edges, and whenever we find out that we have merged, we have two edges that go from different components out of these to this vertex, then we just merge these components. And since these numbers are sorted in increasing order, then the components we merge with this vertex are always just sum of the last components on this stack. So, for example, we can merge Sk minus 1, Sk minus 2, the components containing these numbers, into one together with Ai. And at some point we will either reach the end of the stack, merge everything together, or find out that, for example, Sk minus 3 is smaller than Ai, and at this point we know that all components earlier have all numbers smaller than Ai, and so there is no edge from those components to Ai, and we can stop and continue processing the next number. Then there is a more interesting solution that isn't so straightforward, but maybe is slightly faster, and it's let's say that Ai is equal to 1. Then what we know is that there are edges from all of these numbers to AI. So everything from here is in the same connected component as AI equal to 1. And we can discard everything except the largest of these numbers. So we replace this array by 1 through I, then AI plus 1 AN. So we have just merged all of these first I vertices into one connected component. Then we go on find out where the number, of course, if AI is isolated, if it's the first, if A1 is equal to 1, then we just found one component. There will be no edges from this number 1 to anywhere next, and we can just say that we found one component and continue. If it isn't the first number, then we always decrease this array by 1, or we can say that we deleted at least one number, since we definitely deleted this, and everything out of these except the largest number. And now we can continue find AI equal to 2. If we have deleted it in the first step, then we just continue to the next number, the smallest number in what's left here. And always do this, that when we find this smallest number and know that this number hasn't been deleted so far, then we know that there are edges from that smallest number to all previous numbers. We merged all of it into one connected component, delete everything except the largest number in that connected component, and so on. For this, we just need to know the positions of everything, and it should be doable in linear time, since for each number we just need to remember if we have deleted it and in which position it was, which can be pre-computed at the beginning. And since we are always just deleting some numbers from the end and then adding their maximum, then this array can be implemented as some reverse stack, for which deleting the first number is in O1 and adding the last number, or adding a number at the beginning, is in O1. So this algorithm would be quite fast. Yeah, that's better.
You're welcome.
So then there aren't any really simple problems. It uses a nice trick, and it's been used several times in some competitions, so it isn't something very new. So it wasn't so hard. Problem B is that we have a grid of points, and with size n times m. Each grid has each point in this grid has a cost I and some interesting dense wi, and we want to choose some starting point, then go to some next point in here, for example, like this, this, and this. The constraint is that the interestingnesses must be strictly increasing. They don't have to be good, but in the path we choose, they have to be strictly increasing. So W of this point must be smaller than W of this point, which then this W must be larger than this W must be larger. And we want a path with maximum cost. The maximum cost is the sum of costs of all points in this path plus the sum of distances, where the distances are Manhattan distances. So, for example, from this point to this point, the distance is this plus this. So, x1 minus x2 plus y1 minus y distance, which usually appears in problems. And there is an obvious solution using some suitable data structure, like two-dimensional Fenwick tree or two-dimensional interval tree, segment tree, where we just group all those points with the same interestingness and always compute for each of these points what's the maximum value of, for example, when we have a point x, y, and there are some points on the bottom left, so with smaller x and smaller y, for example x prime, y prime, with total cost of getting to this point equal to uppercase C, then the total cost of getting to this point is this is lowercase ci, then the total cost of getting here is at least uppercase C plus ci plus x minus x prime plus y minus y prime. This would be the basic formula, and since x here is greater than x prime and y is greater than y prime, then this is just this sum, where when we take the maximum of these numbers over all such points to the bottom left of this point, then ci is a constant, x is a constant, y is a constant. We can just take it out and keep numbers. What's left is c minus x prime minus y prime. So total cost to this point minus its x coordinate minus its y coordinate, and yeah, the sum, the maximum of these numbers when they are put in some either Fenwick tree or segment tree, doesn't matter what. In this case, is sufficiently simple in both. Then we just take the maximum of these from points that are to the bottom. The same, we do the same for points that are in this quarter, and in this quarter. And then we take the maximum at ci at ci at the end, and for each quarter we need to add x and y with the correct signs. And this would be an algorithm with time complexity O nm log squared, where the log squared comes from getting some maximum in a rectangle in a two-dimensional structure. But this is kind of slow, and we don't need to do this. It's better to just take just take the total cost like this. So over if we wanted to just loop over all points and take the maximum of this expression, then it would be fine, but it's too slow. So we can notice that the maximum of this is equal to the maximum of y prime. So this would be the first case, ci plus x prime minus xi plus yi minus y prime plus ci plus xi minus x prime plus y prime minus yi, and so on the fourth case. That's because we can write the absolute value as the maximum of xi minus x prime plus, or x prime minus xi. In general, so absolute value of a minus b is the maximum of a minus b and b minus a. And since here we need to take the maximum, here we need to take the maximum, then the maximum expands, and we just need to take the maximum of these four cases. And in each case the expression is linear. A ci is always a constant in everything, so we just take it out, and what's left is to take the maximum of this, maximum of this, maximum of this, maximum of this, take the maximum out of these four maximae and add ci. And for example, when we are taking the maximum of this expression, then it's the same as we described before, that xi and yi are constants, so we just need to take the maximum of c prime minus x prime minus y prime. So the cost of reaching some point with smaller interestingness minus its x coordinate minus its y coordinate, take the maximum of this. Since it's independent of this point I which we want to reach, then we just take their maximum over all previously processed points, and we've got this maximum. We do the same for these four. So what happens is that we just need to keep the maximum of total cost minus total cost plus minus x coordinate plus minus y coordinate. So these are four numbers for each choice of these two signs, and for each point, whenever we process points of a given interestingness, then we go loop through over all these points with given interestingness again and take the maximum and increase the maximum of each of these expressions by that points, whatever this is. And like this, we can see that there is no need for complicated structures. There is no need for separating these points into four quadrants and dealing with these four quadrants as a special case in some structure, but just as for expressions that we compute. And this runs in O(n)m time. It's much simpler to write. It's much there are much less chances to make a bug, and it's faster. So yeah, it's a nice trick to get rid of a complicated algorithm and use a simpler one instead. Then there was the problem Hydra. Hydra was about taking. We have some Hydra with heads of different types. There are n different types. Of each type, we have some number of heads. It doesn't matter doesn't really matter how much is it at the beginning. But let's say that at the beginning we have one head of type 1. And we want to find out, for each head we can either just kill it, and then there are some specific types of heads that appear in its place, or we can destroy it such that nothing will appear in its place. If we do the latter, then it's probably more costly, but it doesn't necessarily have to be. So these types of Hydra heads that appear in place of each head give us some directed graph, where from each type of head is a vertex, and if we destroy it, then there are some different or possibly the same types that appear in this place. The number of edges of this graph is the number of is the sum of sizes of all those lists of heads that need to be deleted, that can appear when we delete some type. So the number of edges is up to 10 power 7 or something. And we need to find the minimum cost with which we need to kill all heads, or in other words, to kill the head of type 1. Since it's basically independent how we kill different types of heads or different heads, we can do a dynamic programming where we compute the cost of killing a head of type I such that there is nothing left after it. Either just destroy it completely and nothing appears directly, or just kill a head of this type, and then there will be heads of new types appearing, and we need to do the same for heads of these types. So we have cost I is the minimum of the cost of slaughtering it, and the cost of queuing it, and sum of costs of completely destroying everything that that appears after it. So we have this formula for dynamic programming, and since this is a graph where we don't have some kind of obvious order in which we should compute all of this, then we need to figure out how to do that. Obviously, if there is a head with cost ui, then nothing appears after it. Then we can just decide that, okay, we know cost I, it's a minimum of vi and ui. Of course, if vi is smaller than ui, then the answer is always vi also. We can just assume without loss of generality that vi is greater than ui for each I. And if there is a head such that there is no, or a vertex such that there is no edge from that vertex, then we can find out the cost of destroying this vertex. And if we found that out, then for each vertex from which there is an edge to that, here let's say there is a cost c, then in this sum we know that one of these terms is equal to c, so we can just discard this vertex, discard that edge, and increase the u of this vertex to u plus c. Otherwise, if we don't know what heads are obviously enough, for what heads is obviously enough to just kill it and be done with it, and nothing appears in its place or anything similar, then we should realize that the cost of destroying any head however we want, doesn't matter which choices we make, is at least the minimum of vi. So any cost I is greater or equal to the minimum of v, because either we just use cost vi or use cost ui plus some of these costs, but each of these costs, so whatever we do, we either create more heads or just have to completely destroy some head, and completely destroying it gives cost at least minimum v. So this tells us that it's optimal to just completely destroy the head with a minimum v, because we know that we can reach cost equal to min v for that head, and there is no way to reach a smaller cost. So if vi equals min v, then cost I is equal to vi. And like this, we can always figure out which head has some cost known. Then we can look at all heads or all vertices from which there were edges to that vertex, to that head, and take that cost for this head which we figured out, and add it to u for each of these vertices. If u plus c for any of these vertices exceeds its v, then we also know that the cost for the head is equal to v, and otherwise we just add that and continue on to the head with the next smallest vi. This gives us the right order in which we should process that all, and the time complexity of this dynamic programming is equal to n plus m, so the size of this graph. Because we always just, if we need to compute this, we just do something for all edges. If we need to backtrack to these edges, the cost of some vertex to the previous vertices, then we always process each edge a constant number of times. and for each head we just compute its cost. So this algorithm is linear in the size of the graph. The problems left were which ones? 1, 2, B. Right, problem C. Problem C is also something that has already appeared in quite a lot of competitions in some variations, and it also uses a nice trick. So we have again a sequence A1 through AN, and we want to change the minimum number of elements of this sequence in such a way that the sum of any k consecutive elements of the sequence is even. So 2 divides AI plus 1 plus and so on plus AI plus k minus 1 for each possible I, so for each I from I to from 1 to n minus k or something, n minus k plus 1. And here the first thing we can notice is that for each number we are only interested in its parity. So instead of having AI through AN, we can just take each of these AI's modulo 2, and have a number that's either 0 or 1. We also only need to change each number by at most 1, either from odd to even or from even to odd. And the trick we want to use here is that we take this sum, and then we take the next sum or the previous sum. It doesn't matter for how the trick works. I plus 2 plus and so on plus I plus k. So 2 should divide this sum, and 2 should divide this sum. So in the resulting sequence, in a sequence where each sum of these k consecutive numbers is even, we should have, when we take this sum minus this sum, the upper sum minus the lower sum, then each number from a plus 1 to ai plus 1 to ai plus ones here and ones here, so that cancels out when we take this and subtract it from this, for example. So ai plus k minus ai should also be divisible by 2. So the parity of ai plus k and ai should be the same. This gives us quite a simple way to just figure out how many numbers need to be changed so that each sum would have the same parity, because by this subtraction we lost information about what's the parity of each sum, only that their parity should be the same. So if ai equals ai plus k modulo 2 for each I, then we can say that this is equal to I plus 2k, ai plus 3k, and so on. So we can group the numbers by the remainder of their index modulo k, and for each remainder all those numbers have to have the same parity. So we need for each of these remainders we need at least minimum of odd and even. if we have OR odd numbers of with a remainder I modulo k, and ER even numbers with that modulo with the index modulo k, then we need to change at least this number of them. When there are less odd numbers, then we change each odd number to an even number. If there are less even numbers, then we change each even number to an odd number. So this sum over all remainders would be enough to just make all sums with the same remainder modulo 2. But in this case, we want them all to have remainder 0 modulo 2, so to be divisible by 2. And of course, if we change all even or odd numbers in the way that ensures this number would be minimum, then it's possible that the resulting first sum will be even. We just need to check it, and if it is even, then the answer is this. And if it's odd, then we need to pick one of those remainders, and well, of course, there is no point in picking more of those remainders and changing more of it from this minimum, but we just need to pick one R, and let's instead of taking the minimum, we need to take the maximum of OR0, ER0. So instead of, for example, changing all odd numbers to even numbers, we would change all even numbers with the remainder to odd numbers. And this would invert all parities. Because in the first sum, of course, all the sums will still have the same parities, and in the first sum we only changed A1 or AR0 modulo k. So the parity of that sum changes from odd to even, so all sums have even parities. And we just need to find out what's the optimal RO. We could, for example, loop over all of them, but it's also enough to just realize that if we have everything in this sum equal to minimum of OR, ER, except for R equal to RO, then, or R0, then it's the answer max of ORO, ERO minus minimum. Because when we subtract this minimum, we just discarded the term in this sum that's replaced by max. So the minimum cost, the optimal way of picking RO would be to pick the RO with this maximum minus minimum, where this maximum minus minimum is the smallest. And this also works in ON. It's since k must be smaller than n, or otherwise it wouldn't, smaller or equal to n, or otherwise it wouldn't make sense. So k doesn't figure in this complexity at all. And C is also solvable in linear time. These old problems from AMPPZ are quite common in this way, that there is often some problem. There are often problems where the complexity can be slightly worse than linear, for example, n log n or something, but the constraints are high, and it's often hard to push through a solution with worse than linear time complexity, but then there is a solution with linear time complexity that passes easily. This is quite rare in most contests, where it's usually that if you have some additional log, then nothing happens. then we have some hard problems plus problem K. Okay. Problem K wasn't so hard. It was about, okay, it wasn't so hard, but none of you solved it, so maybe it wasn't so easy either. It's about having some places on a circle. There are and in each of those places there are some AI rabbits, and we can do the following operation up to k times. That we shoot at one of those places, kill all those rabbits that are currently in that place, and so all rabbits here are killed. All rabbits that were here move here, and all rabbits that were here move here. So there will be 0 here, 0 here, and however many rabbits were here plus here will now be here, and so on. The main problem is that this operation can be done in quite complicated ways, and there is no way to easily move if we do this in some complicated way. That's why we should just find some simple strategy for which it works in a sufficiently simple way. So the first thing to notice is that when we just choose, when we just know that we have shot in some places, for example, like this, then there is no way for any rabbits to move from here to here or from here to here, because we never shot here and we never shot here. So the rabbits can move like this, can move inside these non-shot places, and there is no way for any rabbits that move inside of here to be shot, and there is no way for any of them to move away from it, so they can't be shot anywhere else either. So if we have some two places that haven't been shot, places are untouchable, the rabbits that move inside them are untouchable and nothing can be done. On the other hand, if we have places that are adjacent to each other, then it's often there is often no point in shooting at all of them, because we can just skip this one. If we shot here, then all the rabbits from here moved to here, and then we shot here, so all the rabbits here were killed, and there are also no rabbits here. So there is no point shooting here if we can just chase the rabbits away from here and kill them somewhere else. But it's still a possibility that we could do this if it gave us some more complicated advantage. It's just that it isn't very obvious why it should give us that advantage, and it turns out that we actually never need to shoot at consecutive holes ever. That's because there is this last case where the shot places are always shot place, non-shot place, shot place, non-shot place, shot place, etc. that they alternate. And if we do this, then there is an optimal order of shooting those places such that all the rabbits that were in here are killed. all the rabbits that were between the first shot place in this alternating sequence and the last shot place in this alternating sequence are killed. This order is simply that we shoot here, all the rabbits that were here are killed, all the rabbits that were here move to here, and then we shoot here. All the rabbits that move from here to here are killed, and all that were here originally are also killed. Those that were here move to the next one, and we shoot this one also. So we one in that order in which they are given, and each rabbit from that from each shot place is killed directly, and each rabbit from a non-shot place is killed indirectly if it first moves to a place that will be shot in the next turn. Of course, the rabbits from here, for example, moved here during the first shot, but we already talked about why if we never shoot two consecutive places, then the rabbits that move inside there or tower there are untouchable. We can't ever shoot them. This kind of required us to know which places were shot. It didn't require us to know in which order they were shot, which is a big advantage, because now we can see that the order doesn't really matter, that for each alternating sequence we already know that the order will be first position, next position, etc. And the different alternating sequences are now independent. This allows us to realize that the problem isn't really about choosing an optimal order of places to shoot. It's just about choosing some alternating segments in that circle. So whenever we have some what is it? With for example, A shots, we can kill rabbits from 2A-1 consecutive places, and the order isn't important. We just want to choose some segments of consecutive places toward which we shoot, and we know the number of shots we need. The number of rabbits we kill, we also know that it's the sum of all rabbits that were in such a segment. We can choose multiple such segments. And this means we just need some dynamic programming where we count for shooting some segments up to that place number I. I with J shots. So for such a state Ij, we want to find out what's the maximum number of rabbits killed. Which is just the sum of the sum of number of rabbits in all shot segments. There is nothing in this dynamic programming about any order or anything like that. And this is already a kind of standard problem. There are all NK states, since I is up to and j is up to k, there are two things to solve, because the first thing is that the number of steps we need to solve this dynamic programming problem is squared k, and k are up to some few thousands, so this would be too slow most likely, but we need something like O and k. The other thing is that the places are not in a row, for which it would be simple to just start with I equal to 1 and go to I equal to n, but they are on a circle. So how do we solve this problem with them being on a circle? Of course, j is up to k. Let's take place number 1, place number n, and split the circle somehow. If place number 1 and place number n are non-shot, then it's fine. We just split the circle between nothing happens between these two. The rabbits that are in there are untouchable. Okay, we can just discard place number 1, place number n, and do this dynamic programming on places 2, 3 up to n minus 1. If both places are shot, this is the case which we talked about, that is completely unnecessary, because when we shoot rabbits from one place, they move to another place. And then there are two cases which are symmetric, so we can just handle one of them, which is when place n is non-shot and place 1 is shot. And in this case, we just remember that if we shoot place n minus 1, then place n, then there will be an additional an number of rabbits killed, because if we shot here, then these are also killed according to our scheme which we described before, the scheme of shooting. And if this is not shot, then these rabbits are never killed. So this dynamic programming, when place n is never shot and place 1 is shot, would be done on I equal to 1 up to n minus 1 with some special condition at the end, and with another condition that the first segment we shoot must start at the beginning. This place can't be skipped. So these are some two cases where one of them contains two symmetric cases, because we can just flip all that array if place n is shot and place 1 isn't shot. And then there is still the question of how to do this whole algorithm in O and K. Alright, so cost ij is equal to max of cost I minus 1 j, which is when place I isn't shot and we don't do anything with it. Cost A minus 2j, because if place I isn't shot and the rabbits from there don't die ever, then place I minus 1 also shouldn't be shot, since we want, if the rabbits from there don't die, we just don't want two consecutive places that are shot. So this would be place I non-shot, and this would be place I minus 1 also non-shot, and then there can be some short segments. I minus 2j if I and I minus 1 aren't short, or cost I minus 3j if I minus 1, I minus 2 aren't short. So the maximum of costs I minus 2 and all previous ones, and then the maximum of costs where this place I is short. And everything before it is short. Wait a moment. Now we can do a simpler DP where instead of having just parameters I and j, we can add one more parameter, which is whether the previous place was short. So Sij, there are still O and K of these states, but the states can be processed in a linear time, because either we have cost 1ij is the cost which we get if place I is short, since s equals 1, and we spent in total j shots on it, equal to if place I minus 2 is short, then we spend one shot on place I, nothing on place I minus 1, and place I minus 2 is short, so cost of shooting something up to place I minus 2 plus AI plus AI minus 1, or place I minus 1 isn't short, place I minus 2 could also be non-short, and in this case we have cost 0 I minus 2 j minus 1 plus AI, and we take the maximum of these two options. The option where place I minus 2 is short, and the place where I minus 2 isn't short. The difference is just that when I minus 2 and I are both short, then also rabbits from I minus 1 are short. This is the formula for cost if place I is short, and if place I isn't short, then cost 0 ij is equal to, well, either place I minus 1 is short or place I minus 1 isn't short. So it's the maximum of cost 0 I minus 1 j and cost 1 I minus 1 j. Here we don't add any number of rabbits, because if place I minus 1 isn't short, then the number of rabbits from I minus 1 are added here if they are actually killed. But if it isn't shot, then we don't add those rabbits even if they are killed in at this point of the dynamic programming solution. J is the same, since we don't actually shoot that place I, and we just consider all these both these two possibilities and take the maximum of them. And you can see that these are just constant time, just expressions that are evaluated in constant time. So yeah, this works in ONK, in time linear in the number of states. There are 3 problems left. The geometry is there. One of them is geometry, which you shouldn't solve. One of them is something with expressions that's also quite hard to solve, and the problem formula is possible to solve by guessing and kind of impossible to prove. Polish problems. The time. Oh, okay. I still have an hour. Maybe I can make it. So problem expression. This is the most doable of the 3, surprisingly. We just have some expression written on a line as characters, and it's annoying, but at least all numbers are just 1-digit things, and all tokens, all brackets, and exponentiation sign, addition sign, and multiplication sign are just simple things, just simple 1-character tokens. So you need to parse the expression. I won't really talk about how to parse the expression because it's just some annoying shit. And what you should get is a tree, where, for example, you have an operation plus at the top, and then you have an operation multiplication, 2, and e.g. x. This is exponentiation, and for example, this would be a tree for an expression power of, right? If it's exponentiation, you can just keep the exponent in the same node as that operation. So this would be to the power of 5. Here would be y, 2 times x. So for example, this would be the tree for this simple expression. Each variable only appears once, and it should be a leaf. All the leaves are either numbers or variables. All the internal nodes are operations. And also you can notice that there can be just all number of these variables nodes in this tree, because whenever there is, for example, whenever there is a subtree that doesn't contain any variable, then we can just replace this subtree by its value. We compute everything, all values in this tree, in this expression modulo p, and then we need to work modulo some weird prime. For example, if here is 2 times 4, then we can replace this subtree just by a number 8, for example. So in the end we would have always, whenever we have an internal node, its sums are either internal node or a leaf containing a variable or a leaf containing a number. And if we have two leaves that both contain a number, then we can just merge it, evaluate that part of the expression. And what we want to find out is the number of ways to assign numbers 0 through p minus 1 to the variables of the expression in such a way that the resulting expression evaluates to 0 modulo p. So for example here, so p divides this. Well, it's obvious that the solution to this would be dynamic programming on a tree. It's not obvious how it should be done, especially, okay, we probably should compute for each node of the tree and for each remainder modulo p how many ways there are to assign the variables to that sub-expression, to the subtree of the tree, in such a way that we get some number. Would be some CI, count of ways to assign the values to the expression, to the variables, in such a way that we get this number as the result of the expression. And when we have exponentiation, that's actually the simplest operation, because it's just to the power of a constant, and it's a unary operation, not a binary operation, so we don't need to merge anything complicated. When there are for example, CYI ways to assign to get expression y equal to I, I'll just denote I just use y to denote a sub-expression instead of a variable. In general, well, basically it's the same. It's just that for a variable we know that the number of ways to make it equal to anything is equal to 1. We have exactly one way to assign a number between 0 to through p minus 1 to any variable in order to get that value. So if we have CYI ways to get expression y equal to I, then there are CYI ways to get expression y minus y to the power of 5 equal to I to the power of 5. So for each I, the number of ways to get this I to the power of 5 is the same as the number of ways to get I here. Of course, some numbers y to the power of 5 modulo p can coincide, so we can just take CY5I and make it sum of CYJ such that j to the power of 5 is equal to I. So we just take the required power of each possible value of this expression, each possible I, and add up the number of ways in which we could create those original values to get the number of ways in which we can get we can get any number equal to a suitable power. Then there is summation. Summation is simpler than multiplication here, but they are both quite similar in the end. When we sum up, we have expressions. We have expression x plus expression y. There are cxi ways to get. Let's call this z. Cyi ways to get y equal to I, and we want to find out what's the what are the numbers CZI, which are ways to get this resulting expression equal to I modulo P. And of course, we could try all possible I here, all possible, let's say, J here, and then the value of Z will be I plus J modulo P, and the number of ways to create that would be CXI. This can be also written as CY5 I to the power of 5 CY I. So whenever we get CYI, then we add that to CY5 at index I to the power of 5, and in here we would have CXI CYJ added to, okay, I'll write it here, added to CZ I plus J. So for each I and J we would add to CZ in this index modulo P. The products are taken modulo 30,011. Which doesn't have anything to do with P. This C are, and indices are computed modulo P. And yeah, if we wanted to find out CZK, then this would be the sum over CXI CY K minus J mod P. And this is convolution. This is what I talked about on the first day, and it can be solved by Fourier transformation. In this case, the modulo 30,011 is sufficiently small. The maximum value of this sum would be 30,011 to the power of 2 times P, which is, this would be something like 10 to the power of 9, and P was, what were the values of P? Up to 10 power 5 or something? If P was up to 10 power 5, then this would be approximately up to 10 power, which is enough to just work in doubles, because this 30,011 isn't a suitable prime, or P doesn't have to be suitable prime either for that number theoretic transformation that I talked about, where there is a, where we work modulo something times 2. Here it would be 2 to the power of 16 or 17 or something, 17 plus 1. It would need to be at least like this, but 30,011 doesn't satisfy it, so there is no way. But we can still work in doubles using complex numbers. Now there is multiplication. With multiplication, it's a very similar formula, and I can just make small adjustments here. So instead of plus, I can write multiplication here and multiplication here. And this is the problem, that there is no simple way to invert this multiplication. There would be some complicated sum in here, and not just over all I and all K minus I modulo P like this, but it would be over some weird weird specific lists for each I, and we can't just compute such sums. But we can realize that Fourier transformation uses that I think I talked about that generator. So I talked about an omega such that omega to the power of 0 is equal to 1, omega to the power of k doesn't equal 1 for each k smaller than n and greater than 0, and omega to the power of n is equal to 1. So this would be a generator. Actually, each prime is a generator. It doesn't have to be just in the form 2 to the large power times some odd number plus 1. And we want to find this generator for numbers modulo p, not modulo 30,011. We want to find some omega, which is a number, an integer modulo p, such that this holds. And then we can write every number using a power of this generator. In this case, it would be not n but p, because they are modulo p. So any I can be written as omega to the power of y of I prime, j as omega to the power of j prime, and then I times j would be omega to the power of I prime plus j prime. And already we can see that there is some hope here that the exponents, instead of having an addition, instead of having multiplication, we can just have addition here. And since the generator has this property that it's not equal to 1 for any k between 0 and p minus 1, between 1 and k minus 1, then it can be proved that for each I there is a unique I prime such that this equation holds. So going from indices I to indices I prime would be basically just permuting the numbers in each of these arrays. And we could compute a permuted array Cx prime, permuted array Cy prime, and then try to obtain a permuted array Cz prime. And from this array we could use the reverse permutation to get Czi for each I. So the formula we would use is basically the same. It's just that Cx prime I Cy prime j should be added to whatever corresponds to Cz I multiplied by j modulo p, since this was I prime j prime k prime, then I prime plus j prime, well, I times j is omega to the power of I prime plus j prime. So just like I prime corresponded to I, j I prime plus j prime will correspond to I multiplied by j. So Cz I prime plus j prime, again modulo p. These numbers are also computed modulo p, since omega to the power of p is 1. Was it p minus 1? Not sure. No, it's right here it should be p minus 1.
Yeah.
Yeah.
It's p minus 1 minus 1. It's model p minus 1.
Yes, it's modulo p minus 1 because I just realized that I work modulo p all the time here, but it should be p minus 1, and since this is modulo p, this is modulo p minus 1. Here we always work modulo p minus 1. This is due to Fermat's little theorem, and this means there is something we are missing here, which is C0 or C0 or p minus 1. This formula works only for ij non-zero, so that this would be also non-zero. And if we want CZ0, then we just take the sum over all I equals 0 or j equals 0, but this is just computable in linear time. So CZ0 separately, and for all indices not 0 through p minus 1, but 1 through p minus 1, here and here and here, we have this generator that gives us a permutation of indices from 1 to p. Okay, not a permutation because it's from 1 to p minus 1 to 0 to p minus 2. If I is between 1 and p minus 1, then this is up. Then I prime is up to p minus 2, so is this transformation of indices, and here we work modulo p minus 1, so the indices are up to p minus 2, and then we just use this bijection to get an inverse bijection, inverse transformation, and get from CZ prime k prime to CZ k for each k from 1 to p minus 1. This is actually everything for this problem, and the time complexity would be number of nodes in this tree times p times log p, because this is the time complexity of one Fourier transformation. This is done again using Fourier transformation. How to find this generator? It can be done just by brute force in theoretically OP squared time by just trying all possible omegas from 1 to p minus 1 and trying to get all of each omega's powers, and whenever we see that there is a power equal to 1, then we stop, or there is a duplicated power, then we stop and try another generator. And if we reach the situation where all powers, all the p minus 1 possible powers are distinct, then we have found the generator. There is quite a big chance that we stop sufficiently early for those numbers which obviously aren't generators, or that the optimal generator is sufficiently small. So while this would be in theory OP squared, then in reality it has a good chance of working fast. There are a lot of tricky problems where you can just push through some solution that is suboptimal because the number of states it would reach is very small. Let's keep geometry for the last for last, and I'll now explain how to solve the Formula 1 problem. Formula 1 was about having some race where cars start car 1, car 2, car 3, n-1, and n. And we know that that car I should overtake the previous car. So, for example, car 4 should overtake some car A 4 times, car A1 should overtake some car A1 times, and so on. And it's possible for two cars to overtake each other multiple times. It's possible for the result of the race to be whatever we want, but we just need to find out if it's possible to get exactly this sequence of overtakings. So car I should overtake other cars exactly AI times in total. Yeah. The official solution is to compute some numbers sk, such that sk is the maximum possible value of ak if we know a1 through ak minus 1, ak plus 1 through an. So all other numbers in the sequence except ak would be known as, and sk is the maximum possible value of ak. It's obvious that if the answer is yes, that if this is possible, then sk is greater or equal to ak, because it's the maximum possible value of ak. And if any of these inequalities are violated, then the answer is no. The question is whether if this holds for each k, then the answer is yes, and supposedly it is. There is no proof given. And I have no idea why it should hold. Maybe, well, you can think about it, you can try to prove it. But in a contest, okay, you have found some conditions, and if you can compute these numbers sk sufficiently easily, then it's good enough to just guess that maybe it will work. There is still the question of whether you should put some effort into thinking about how to solve this problem if it's because nobody has solved it. But if there is nothing more to do, if you're at the end of a contest and you still have a chance to code this and check these conditions and give the answer yes or no based on that, then why not do this? There is nothing to lose. There were two teams that solved this problem in the official contest, in that AMPPC in 2012. And I'm guessing that they also just tried an educated guess. Or something else. But proving something like that would be quite complicated, and it's often enough to just try to intuit whether whether some conditions like this would be sufficient. There would still be a lot of numbers to compute, and there is also one lemma given that let m be the last, let's see what it was exactly. Let m be the last car for which it's impossible, for which either that car must overtake, well, let's say am, for each overtaking of any cars which are before that car, so am minus 1 up to a1. Then whenever this car overtakes some other car, then that car must be car am, and it happens like this, that am overtakes am minus 1, then am minus 1 overtakes am, m minus 1 overtakes m minus 1, m minus 1 overtakes am overtakes m overtakes m minus 1 each other. In total, am minus 1 plus 1 times, because there is one time where m gets before m minus 1, and then am minus 1 times where m minus 1 gets again in front of car m. So this happens in total am minus 1 times. One times, and then there is then car m gets again in front of car m minus 1. So in total there are am minus 1 plus 1 such situations. At the end of this there is car m before car m minus 1, then there is car m minus 2 here, and the same situation as happened here, that these two cars will overtake each other m minus 2 times, and then there will be one time where car m overtakes car m minus 2 again, and so on. So if we computed this total number, sum of am minus 1 plus 1 plus am minus 2 plus 1 and so on plus then either this is equal to am, or am is even greater than that. So either car am participates in just alternating overtakings with everything before it, or it has to participate also in an overtaking with some car that's after it. So for example, car m minus m plus 1 overtakes car m, and then car m again overtakes car m plus 1, or otherwise it wouldn't be possible to produce this sequence. Then if this is true for car m, and it's the last car for which this is true, m such that this will be denoted later as am minus 1 am. So if small a lowercase am is greater or equal to uppercase am, then we know, well, the organizers give a theorem or a lemma that if m is the last car for which this is true, the largest m, then for each k not equal to m, we have sk greater or equal to ak, that this is true for any car, definitely true for any car except this mth car, if it's possible to create this sequence. And so we only need to check whether Sm is greater than Am. So this would be just one number which we need to compute. And it's actually not that hard to compute this number Sm or any Sk, because here we have shown that this is takings in which this car can participate, in which car M can participate with cars 1 through M minus 1. So AM is the maximum number of overtakings between smaller index cars, so cars that start earlier, and car M. And then we want to compute that another number, BM, number of overtakings where AM overtakes one of the cars that started after it. It might not be possible to get any such overtaking, possibly. For example, if the cars that started after this M car have all AM plus 1 is 0, AM plus 2 is 0, up to AN, which is 0, then there is no way for any car, any of these cars to get to get in front of AM, in front of car M, so BM would have to be 0, because car M wouldn't be able to overtake any of these cars again. And it's clear that as M is the maximum number of total overtakings, so it's AM plus BM, because this is the maximum number of overtakings with cars smaller, and this is the maximum number of overtakings with cars larger. Is of course just an upper bound. It's not necessarily true that if there is an well, it's not obviously true that if we have some Sk which is an obvious upper bound, then it's possible to actually reach that Sk with that given sequence. But yeah, that we have a claim that if there is some Sk, then it's always true to reach that. That it's always possible to reach that. It's always true that such a sequence exists if all those inequalities are satisfied. So now we want to find this number BM. With okay, we can compute some numbers lowercase b m plus 1, lowercase b m plus 2, lowercase b n, and here we have Bi is the minimum number of overtakings necessary for car I to get immediately after car M. So afterwards we can do this scheme where car M and car I overtake each other repeatedly, and if car I takes Bi overtakings at least to get a situation where we have car M and then car I, so that we could have IM, MI, etc. Then when this happens, we have the remaining number of overtakings where I overtakes M is A I minus BI because we already spent BI overtakings so far. So there are is it before or after? Yeah, that's fine. If we have this situation and there are AI minus BI overtakings left, which we can use for car I, then we can do this thing exactly AI minus BI times. So if this could happen, then we have then we are adding the number of overtakings where M overtakes I increases by AI minus BI. So uppercase BM. Of course, if BI is smaller or equal to AI, then there is no way to do this any number of times. So BM is equal to the sum over I of max of 0 and AI minus BI. So if we could compute these numbers B, M plus 1 through M, then we can just compute the sum. Since it's easy to know AM, then we could compute AM plus BM, compute SM, and finally check if this inequality is true for M. And by this find out whether the answer is yes or no. So there's a lot of consecutive steps. And finally, all we need to compute are the numbers BI. How do these work? Well, of course, Bm plus 1 is equal to 0, since there is nothing car M plus 1 needs to do to get immediately after car M, because that happens at the beginning. B M plus 1 equals 0, and then we have Bm plus 2 which is Bm if AM is Bm plus 1, M plus 1 is smaller or equal to Bm plus 1. Or B M plus 1 or A M plus 1 if Bm plus 1. So this recursive formula, okay, instead of just writing Bm plus 2, I'll write Bi plus 1, here Bi, 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 So this is actually just the maximum of AI and BI. Yep. Yeah, the maximum of AI and BI. These two cases appear, well, this is when in order to get a car number I immediately after car M, whenever, if this happens, we take at least as many overtakings as there are available for car I. So there is nothing else that can happen after this, and there is no way to get car I in front of car M. So in order to get car I plus 1 immediately after car M, then we need car I plus 1 to overtake car I. And then we have the same situation as there was for car I, so the number of overtakings car I plus 1 needs is the same as car I would need. But if it's possible to get car I immediately after car M, and then car I can still overtake car M, then it's easier to get car M plus 1 immediately after car M. Because car I will be before car M, and we only need those AI overtakings. This whole problem, it was expected to be the hardest problem in this contest, and as you can see, just based on the claim that, based on these claims, that is basically magic. And okay, it's possible to explain why computing AM and BM, uppercase AM, uppercase BM, and lowercase BI works, but it's completely unclear whether this is just a very loose upper bound, or if it actually gives something useful. So yeah, these problems are not very solvable. These hardest problems in Polish contests. So let's just say that this is how it works, and not worry about why it works. What's left is the geometry problem, which is at least sufficiently understandable. So we have some points on a plane, and there are n points in total, and it's something like 10 power 5, and we have two types of points. Some of them are already fixed in the plane, and there are some candidate points where for each candidate point we need to find out what's the area of the convex hull created by those fixed points and the candidate point. So there are m candidate points, and for each of them we would basically need some O log n algorithm to get the area. So obviously the convex hull of the fixed points and the candidate points is the convex hull of the convex hull of fixed points and the candidate point. So we want to find the convex hull of the fixed points first. And now for some candidate point, the new convex hull is created by making a line to some one vertex, another vertex, and instead of having this hull, we would have a simpler hull. what's the area of this? How well, if we can compute the area of this part that's cut off between, let's say that this is candidate vertex I, this is fixed vertex AI, and this is fixed vertex BI, then we need to compute the area of this cutoff part of the original, and then add the area of the triangle. The area of the triangle is easy to compute. It's just vector cross product. It's somewhat more difficult to compute the area of this cutoff part, but that's doable by just computing some prefix sums. For example, the prefix sums are basically sums of this part, of this part, of this, and so on. And wait, how did this work? We would need to compute this these areas of the cutoff parts or areas of this part, but the harder part is how to find out which points are which are the points AI and BI. The official solution uses some trick where we pick some arbitrary point inside the convex hull. Of course, there can be some candidate points inside the convex hull, and for this the area of the resulting hull is the same as the area of the original hull, but we pick some arbitrary point inside this hull. It doesn't have to be even one of those fixed points or one of those candidate points, and find array from this point to a candidate point. Find out which side of the original convex hull is intersected by this side. Is intersected by this ray, and this can be done using some binary search, checking whether we are getting closer to the ray or farther. And now let's imagine that we are finding we are looking for AI, and for each side of this polygon we extend it in one direction, in the same direction for each side, and we are looking for the first pair of these extended sides, such that I is on this side of one of those extended sides, but on the other side of the next of those extended sides. So in this case, AI will definitely be this point for which it was the last for which this candidate point was on for the last time on the original side of this extended half line. And as you can see, when I is on the other side of this, then this ray is intersected by the extended side by this half line. So we are looking for the first half line, or for the first side of the polygon that, when extended, it intersects the ray to the candidate point. And since for the convex polygon, this extended size, this extended half lines always go in increasing, always have increasing angle with respect to some radial coordinates, then we can also binary search for this first side, and therefore for the point AI. When we are looking for point BI, then we extend all sides again, but in the opposite direction. So this side would be extended like this side would be extended like this side like this, and it can be seen that this extended side is the one that intersects the ray, and therefore BI is this point. This, since it only uses some complicated geometry and binary search, it would run in all, if there are n candidate points and m fixed points, or the other way around, it will run in all n plus m log n plus m. I'm sure there are many ways to find out the area of this cutoff part, but there is nothing about it, basically nothing about it in the official solution, and it's geometry, so I don't want to even think about it. There is still some time left, and I'll be talking without pause for 3 hours. But we started some time later, so I'll talk about some easier, nicer problems that, like I mentioned, that problem with sorting a permutation, but the cost of each swap is the sum of two numbers in that permutation that are swapped. Then not so far ago, maybe some 2-3 months ago, there was in cold forces a problem which reminded me of this. It was also about sorting a permutation, but instead of having just swaps allowed, we could just choose some. Okay, we have. AN, and we can choose some AK1, AK2, AKM, and move this number to this position, move this number to the next position, etc., and move this number to this position. So instead of AK1, we would have AKM, and so on. We could cycle the numbers like this. The question trained that we can make basically any number of these cyclic shifts, but we want their minimum number with the constraint that the sum of m, the sum of sizes of these shifted cycles is bounded by some number s. And this has a surprisingly simple solution if there is no such bound. Of course, if there is a number ai equal to I, then we don't need to do anything with it. If there is just one cycle in this permutation, then we can just suitably shift that cycle. And we would only need one operation, because, for example, we would move AK2 would be equal to K1, AK3 equal to K2, etc., and K1 would be equal to Km. So each number would get to the right position in just one cyclic shift. But if there are multiple cycles, then it's possible to sort everything just by reordering each cycle, just like that, solving the problem independently for each cycle. But that's not the optimal solution. The optimal solution uses just 2 cyclic shifts. If we don't have this, then there are always up to 2 cyclic shifts necessary. So if we have 2 cycles, for example, 3, 1, 2, 5, 6, 4, then the first thing we want to do is to just chain all cycles together and make one cycle out of them, and then for that cycle we can just we would have just 2 operations in total. And what we do for that is similar to as I talked about, one swap being the same as merging 2 cycles. Well, we want to merge all cycles, so we want to find out which swaps we need to make to merge them. For example, swap 3 and 5. Of course, when we find swaps, then we can just find out what permutation these swaps make, and that permutation is whatever we need to do that to merge the cycles. So we have, for example, this, and the permutation graph of this would be 1 to 5 to 6 to 4 to 3 to 2 to 1. So in this case, we would just need to swap 3 and 5 and do that cycle, and then we would just apply that one operation. The harder part is what to do if we have this constraint, because what's the total cost of this? Of course, each number must be moved at least once. Each number ai not equal to I must be moved at least once. So if s is smaller than that number, then nothing can be done. But the total number of the total size of these 2 cycles used in these two operations is equal to the number of these ai not equal to I plus the number of cycles in them, because the first operation was chaining some C cycles together, and the second operation was just okay. So the first operation had this cyclic shift in a cycle of size C, and the second operation had a cyclic shift of all numbers ai not equal to I. So the total size would be that, and this gives us a constraint that we can't chain together more than s minus number of integers ai minus one cycles. So only this many cycles can be merged, whatever operations we perform. And yeah, this means we can compute the number of cycles we will have in the end if we, for example, merge those cycles using one operation. Then the total number of operations will be equal to 1 plus that number of cycles, because in the end we have this limits us as to how many cycles as to the smallest number of cycles we can have, and then for each cycle we perform one operation that sorts it, and this doesn't add anything extra to that sum of m, unlike what the chaining of cycles did. So the total number of operations would be that minimum number of cycles we can get plus the number of these. That problem was, I think, around 500 or something. It was based on an Olympiad, so it shouldn't be too hard to find. And it was problem E out of 6 problems, A to F. Okay, so this will be everything for today. I've gone through all problems of yesterday's contest and talked about one more, and I have enough for today, so let's see you at the contest.